Hey everybody, Dr. Retzek here. This is our second video on section 6C, where we're going to continue the discussion of orthogonal complements. Let's get started. So remember, the setting is this at the moment. You have an inner product space, call it V, and this is equipped, as usual, with some kind of an inner product, but it's abstract. We don't have anything in particular in mind. All right. Now, sitting inside V, you may have a subspace, let's say U. So in this discussion today, U is indeed a genuine subspace. It is true that you can formulate the notion of orthogonal complement for a mere subset, but today, U is a subspace. So U looks like this, and in particular, since it's a subspace, we know zero's in there. All right. Also, since it's a subspace, that means U is a vector space in its own right. And if everything is finite dimensional, which it is in today's discussion, then that means U possesses an orthonormal basis. So let's write down an orthonormal basis for just U. So let's say it's E1, E2, through EM. And let's take note below the diagram that here, E1 through EM is an orthonormal basis for U. Okay. We want to think about the role that this subspace U plays in the structure of the larger space V. So imagine a vector V belonging to the big box, but not necessarily belonging to the subspace U. So let's just take a little v in big V. The claim is that that vector little v can be realized as a piece from U plus another piece. And the way to do it is to exploit the orthonormal basis for U. So let's go like this. Let's see what happens when we build this combination of the basis vectors for U, where we get the coefficients through inner products with V. Now, there is no reason to believe that we are done writing this expression down. After all, look at our picture. If we were done writing that expression and that were literally an equal sign, then we would have V written as a combination of E1 through EM, which means V would belong to the red blob U, which in our drawing it clearly doesn't. So you have to balance the books here. But I think it's fair to say this. Certainly that's true, because we just wrote V as blah plus V, take away blah. So algebraically speaking, this is a clearly true statement. The virtue of writing this arbitrary vector v in this way is that this piece is an element where? Look back at the picture. Do you see that that chunk belongs to U? And this other chunk we could just name that piece W. So that's some vector. I don't know where it lives in the big box, but it's some vector. Just call it W for a minute. So that whole second chunk is called W. Now this W is interesting relative to the subspace U. Can we see what happens when we take the inner product of W with E1, say? Notice, if you take that whole second chunk and inner product it with E1, let's look at what happens. All right, well, W is a big linear combination of things. But remember, we have additivity, homogeneity in the first slot. So even though W is that big thing, it kind of comes down to what each little piece of W does when you inner product with E1. So let's go through the pieces. Okay, so that V right there, that's going to inner product with E1. And then this piece right here, that's going to inner product with E1. But hang on, when this object inner products with E1, well, the scalar you can pull out in front from homogeneity. So you just get inner product of V with E1 sitting out in front of inner product E1 with E1. But what is the inner product of E1 with E1? It's just 1 because the E's are orthonormal. So when that second piece hits inner product with E1, we just get VE1. Now the remaining pieces, each of those is one part of the vector W, and each of these will also inner product with E1. But when you inner product E2 through EM with E1, nothing happens because the E's are orthonormal. So E1 inner product with any combination of E2 through EM is simply 0. So those other pieces contribute nothing. And lo and behold, when you do W's inner product with E1, you just get 0. In fact, if you run that argument, you find that W's inner product with any EJ is 0. Okay, so hang on a sec. So W turns out is orthogonal to every basis vector for U. Thus, W is orthogonal to any vector in U, because any vector in U is just made up of those basis vectors. So if you have something orthogonal to every basis vector, you have something orthogonal to every vector. So that second chunk actually belongs to U perp. Now look back at this expression. We started with an arbitrary V in our inner product space and have successfully written it as a thing from U, that's the red piece, plus a thing from U perp. We just went through the argument that W belongs to U perp. So that means every vector in the big box can be written as something from U plus something from U perp. In other words, the vector space is the sum of U plus U perp. And since the intersection of U and U perp is already known to us to just be 0. Remember, 0 is the only thing that's orthogonal to itself. I think all of this goes to show that the direct sum of U and U perp is the whole space. So that's a theorem. We just proved it. We just proved that if U is a subspace of V, then V is equal to U direct sum U perp. So you can always break down the structure of a big inner product space as a direct sum subspace plus subspace perp. All right, and notice, by the way, that means if everything's finite dimensional and you knew dimension V and you knew dimension U, now you know dimension U perp. You just subtract U's dimension from V's dimension. Because in 306, we learned that's how dimension works with direct sum. So the dimensions of U and U perp add up to the dimension of V. All right, so that's one nice structural thing. The box V is in fact the direct sum of U plus U perp. All right, the only other thing we want to achieve today is to think about something kind of funny. What happens if you have a subspace, you take its perp, and then you take the perp of that? Now, instinctively, I want to say stuff like this to myself. Well, if you take everything that's perpendicular to U, and then take everything that's perpendicular to that, you get U back, right? Like it seems right, like when I'm picturing, the three-dimensional world we walk around in. That makes sense to me. If I'm in my living room and I say, all right, what direction is perpendicular to the floor? And I say, oh, vertically. And then what is all the stuff perpendicular to that vertical? Well, it's the floor. I get it in our normal sort of classic Euclidean finite dimensional space we walk around in. But it's actually true in abstraction, and so that's our second fact. So let's draw another picture, and let's see if we can get our hands on why U is equal to U perp, which is fun to say. All right, so again, the setting. You got a big old inner product space V. This V. This is equipped, as usual, with some kind of inner product. Okay. Now, you got a subspace hiding in here just like before. Let's draw it in red. Let's draw it, say, right here. So there's U. Okay. And then let's put U perp on this picture. So U perp is maybe like this. And we know from the previous example that the direct sum of those two subspaces is the entire box. And remember, those two subspaces, they only intersect at 0. That's why I kind of try to draw their boundaries as sort of just brushing up against each other. So maybe 0 is right here. That's the vector upright oval. Okay, and now we're going to try to argue this claim. The claim is that U is equal to U perp, perp. It's an appealing claim. It makes sense to us, but we got to prove this in abstraction. Okay, so let's run through this proof. That equal sign is equality of sets. So in a math 248 kind of way, we're going to do subset both directions. One direction's easy, the other direction slightly less so. Okay, so let's go this direction first. Let U belong to big U. Okay, so U's sitting right here in our drawing. There's U. Okay. Then the inner product of U with W comes out 0 for each W in U perp. Now let's make sure we believe that. If W is in U perp, so on our picture, W's over here, okay, well, how did it get into U perp? W got into U perp by being orthogonal to everything in the red. In particular, W is orthogonal to U. So U inner product with anything from U perp is 0. And that means U is orthogonal to all of U perp. So that means U belongs to U perp perp. Whoops. U belongs to U perp perp because we just showed it's orthogonal to everything in U perp. Okay, let's do the reverse containment. Okay, so in the reverse containment, we have to take an object in U perp perp and argue that it belongs to U. Okay, so I'm going to draw, based on the first containment, now we know this. U is definitely a subset of U perp perp. So U perp perp might look like this. In home. No pun intended. Purple. Ha! I slay me. Okay. So this purple one is U perp perp. U perp perp. Okay. So let's take an object in U perp perp and try to argue that in fact it belongs to U. Okay, so here's what we'll do. Let's take an arbitrary object in U perp perp, call it, say, V. Let V belong to U perp perp. Okay, so there's V. Now, the previous result of this video tells us that big V is the direct sum of the red and the green, which means V can be written as something from the red plus something from the green. I'll use U and W again. Where U belongs to the red and W belongs to the green. We know that it's possible to express V as a sum, something from red plus something from green. Okay, fantastic. Now look at where V minus U lives. Then V minus U, okay, well that's a thing in the purple, take away another thing in the purple, So that's definitely in the purple. But also, wait, V minus U is W. And W's in the green. Wait, hang on a sec. So V minus U is simultaneously in the purple and in the green, but the purple is the perp of the green. Purple is green perp. And you know that a thing belonging to a subspace and that subspace is perp, well, there's only one thing that belongs to both of those. It's 0. So V minus U equals 0, i.e. V equals U. And where did U live? In big U. So we started with an object in here, and we argued that it lived in here. So U perp perp is indeed a subspace of U. That's the reverse containment. That's containment both ways. And we're done. So the moves in there are kind of fun, and they involve sort of definition of perp and making sure you know about subspaces and how and where they overlap, etc. But the real prize is the statement itself. The real prize is here. This is gold. If you take something and perp it and then perp that, you get the subspace U back again. Okay, so that's it. We had 2 main objectives today. First one was to show that if you take a subspace U, V structurally is just the direct sum of U with U perp. Second thing, if you do the perp and then perp that, you get the subspace that you started with back again. Okay, so we're learning stuff about orthogonal complements. This will pay off in a big way here towards the end of section 6C. All right, that's it until next time. Bye.